So today I will bring in vector bundle valued forms so we can do differential geometry in a coordinate free manner, intrinsic geometric coordinate free manner. But before I do that, I want to say a few things about what last time and kind of sum up something about that. So one is that I forgot to do the Delaunay case. So we said that we'll assume that all triangles are acute, or the tetrahedra, or whatever simplicial complex we have is well centered, which is a very restrictive condition. So instead, one can do, if you have a mesh which has, where every pair is Delaunay, and let's not worry about the boundary in this discussion. So every pair of, let's say, the triangles or tetrahedra is Delaunay. So Delaunay means that if I draw the circumcircle of any one of the simplices, so strictly Delaunay means that no other vertex will be in that sphere, in that circumsphere. So for example, if I draw the circumcircle of that, it should not contain this vertex. So in 2D, and this works for surface meshes also, because you look at things pair at a time. So you can just flatten them and check that condition. And for 2D, that amounts to the fact that the sum of the opposite angles across from each edge should be less than pi, strictly less than pi. And when you have that, a wonderful thing happens, which is that the circumcenter of the left guy ends up being on in the right place. The circumcenter of the left triangle is to the left of the circumcenter of the right triangle. And so even though it's outside, they are in the right order. And so we were kind of inspired by D'Arcy flow simulation that we were doing, that pressures were living in the circumcenters and the fluid was being driven and the flux is being calculated on as one form on the edges. And so if they are in the right order, the fluid will be pushed in the right direction. If they were flipped, then things can go bad. So in fact, that turns out to be right, that if what you do is you do a signed length. So this is negative because it's outside, the circumcenter is outside, and this is positive. So you get a net length which is like this. And this also works for higher dimensions, for looking at areas, volumes, and so on. So this we call Delaunay Hodge, because for Delaunay meshes are very commonly generated. Most mesh generators will give you a Delaunay mesh. That's why, that's what a lot of development in computational geometry was in the meshing community. So anyway, so that kind of makes it possible to use a more general class of meshes. And they have to be strictly Delaunay, because technically in Delaunay, you are allowed to be, the other vertex is allowed to be on the sphere, but if you disallow that. So that's one thing. The other thing is that, so when I said this has dimension so and so, what I meant was that it's locally, your local dimension is, because this space it's an infinite dimensional vector space, but at every tangent plane, its dimension is n choose k. So normally one would write that it's this set of k covectors on the tangent space. So at every point, this object has dimension n choose k. Okay, the third thing I want to say is that the word discrete X-ray calculus is sometimes used in a variety of senses, but I just want to say how we think of, when we say DEC, this is what we mean. The important parts are that there is a D and odd star separation. So the D and the metric, the derivative and the metric are kept separate. So you saw those kinds of diagrams where we had like C0, C1, C2, and these were Ds, and then there were D0, D1, D2. And there were hot stars going between. So this is the picture we think is an important part of DEC. So if you go down the path of the metric dependent part, then the other next feature of DEC is that it uses circumcentric duals. And then it uses that to define the discrete hot star as the dual, the volume of the dual divided by volume of the primer. And on the other side, in the metric free side, D is coboundary. And wedge is anti-symmetrized cup. And a more recent but important thing is the naturality, which is also kind of metric dependent. So that naturality with respect to simplicial maps. So for us, this is the strict definition of when we say DEC, this is what we mean. So now we are going to do vector. Yes.
Can I ask a clarification over here?
Yeah.
So when you're saying that the D and the metric are separate,
yes,
in the language, in the sort of differential continuum differential geometry manifolds principle, so is this the same as saying that the connection and the metric can be specified separately?
No, this is much simpler. There's no need for a connection because we are only doing real valued stuff. But this is actually a feature of just smooth manifold, calculus on smooth manifolds has this exact same feature. So in contrast with finite element, where typically you don't separate the two, you just think of the inner product when you're computing the stiffness matrix.
But when you have one forms or two forms, then for them, you do have, there is a fine connection, right?
No, you don't need a connection to define. So smooth manifold structure, differentiable structure doesn't require anything other than.
No, for the if you want to paddle transport or you want to compare them at two different locations.
No, but these are real valued things.
Okay, that's right.
So till now we were doing real valued. Okay. So today we start doing something where we need that additional structure. So these for us are essential features of, if you want to call something DEC. So so now let's talk about vector bundle valued DEC. So this is relatively, I mean, it's definitely newer. And it's not well tested in code because we haven't programmed it. So, and it's not complete, but I'll present a fairly complete picture. But before I present vector bundle value DEC, I just want to recall this view of differential geometry, which is coordinate independent without any Christoffel symbols and coordinates, because that's what we will discretize, because that turns out to be relatively easy to discretize. So let's talk about vector bundles with connections first. This is first smooth stuff. So again, we will take smooth things, we'll think of them intuitively, not do a very formal definition, but for the discrete things, we'll be more precise. And a vector, so let's say you have a manifold M, and E is a vector bundle over M, which for our purposes, it's enough to think of, you have a like dimension D vector space glued at every point. So there's, the technical definition will have more things like local trivialization, restriction to a point is of the homeomorphism is a linear map and all that. But we don't need all that. So the picture to keep in mind is that you have a manifold and you have a vector space of the same dimension stuck everywhere. And so the thing is that you can't do derivatives of vector valued things with just this structure, because they, so let's say you have a sphere, I'm sure you've seen this common example that if you start here at the North Pole and you take a vector and transport it, and then you move along the equator and then you go back, then you get the vector turns, and how much it turns depends on the path you take. So for taking derivatives, you have to compare things in different places and take the limit. So where are you going to approach it from? Which path are you going to take? So you need additional structure besides just the structure of the vector bundle, and that structure is given by a connection. So a connection is the linear map. So let's say, first, let me just write some notation. So this notation gamma E is kind of standard for section of a vector bundle. And that just means, just have in your mind the picture that, so you have these vector spaces everywhere, section just picks out a vector from every place. So like a vector field, so tangent bundle is an example of a vector bundle where the vector space is the tangent space of the manifold. And taking a section of the tangent bundle is picking a vector field. So similarly, just have the picture to have in mind is that the objects here are things which you get by picking one vector in each spot from E. So connection is a map. So we'll put E, the connection corresponding, sorry, the connection is just given to you as a structure. And this connection is a map which maps the sections to sections of T star M tensor E. So I'll explain what this notation means in a second. But again, we have a very simplistic view of that. You don't have to worry about formal definition of what this symbol means. I will use it in a very intuitive way, but all of this can be very, very formal. So it has the following properties. First of all, it has linearity. So if I have two sections and a constant, so if I do nabla E of C1S1 plus C2S2, I'll get the usual thing. And that it has Leibniz. So if I do a function, times a section, so S is an element in this. So we'll take S, S1, S2. These are all elements in this. So these are all sections. F is a smooth function on the manifold. And you just require linearity in Leibniz. So Leibniz here says that this is equal to dF tensor S plus F nabla ES. So notice that that's a one form. So things that live here look like this: one form, funny symbol, tensor product symbol, section. So what this means is that so things, and this one is a one form, is a vector bundle valued one form. This thing lives here by definition, and F just multiplies that. So things that live here so if you have alpha, so objects in, so this thing, this space, this contains linear combinations of terms like alpha tensor S, where alpha is a one form, ordinary one form, and S is a section. So if you give it a vector field, so if X is a vector field, then, and if you give this one form, this vector field, you just get this alpha consumes that, you get a function. So this becomes a function, and you get a section. So, and the covariant derivative has the same data. So if you fix an X, then the covariant derivative of some section S along X is just, so we'll write it like this, and it's just do this and feed it that. So we said this guy lives here. So it's a one form, E valued one form. So when you give it a vector field, you get a section. So this covariant derivative, therefore, for a fixed x just maps sections to sections. So the first time I learned differential geometry was taught like that. And it was very annoying because I had no pictures in my head. This looks very abstract and axiomatic. So then I struggled with the rest of the world and realized that that was not any more illuminating. So finally, when I did the discrete version, then I realized, okay, this is why the axiomatic thing, because the discrete picture is so simple, you will see that this axiomatic definition will start making sense. So we have this object, and why work with connection rather than covariant derivative when the information is the same? And the reason for that is that this covariant, so connection picture generalizes, allows us to generalize to exterior covariant derivative. You get a whole family. So this D nabla K will go from E valued K forms to E valued K plus 1 forms. So, and what are objects which live here? Very much like the ones that were in omega 1. So another name for this space is omega 1 M semicolon E. So E valued 1 forms. And this is just the generalization of that. So things that live here are combinations of objects like this, where alpha is a K form. S is a section as before. So if I give you K vector fields, alpha will consume them, you will get a function, so you'll get back a section. So this is the sense in which one defines K forms. And so this D nabla should have, again, linearity in Leibniz. Everything is defined axiomatically like that. So it should be linear and should have Leibniz. By the way, I should point out one thing here, which maybe we don't need, but so this guy has Leibniz in this slot and C infinity linearity in this. So you can have, I can take a function, and you can see that if you trace back what this definition is, because this is a one form. So when you take a function times a vector field, the one form just worries about the vector field, the function just multiplies it. So that's why even for a function here, you get linearity. But when you do a function here, you have a Leibniz rule. And the Leibniz rule is take directional derivative of f along the vector field, which is a well-defined concept, times the section plus f times nabla Ex of S. Okay. So how is this defined? Well, you again require linearity and Leibniz. I'll stop writing linearity, but maybe mention the Leibniz here. And the Leibniz here is that if I do D nabla of some alpha tensor S, then, so this really helps in calculations. Then this is D of alpha tensor S. This is the ordinary D because alpha is an ordinary form. Plus -1 to the degree of alpha. If it's a K form, this will be K. Alpha wedge nabla E. So that's a one form. It's a E-valued one form. So when you wedge it with a K form, you get a K plus 1 form. Alpha is a K form, so D of that is a K plus 1 form. So at least typographically, this makes sense. And what does this mean? You can imagine that this is a E-valued one form. The alpha wedge only wedges the form part of it. It doesn't touch the section part. And you can do a completely coordinate-free definition using feeding it vectors, but you see what the picture is. So it turns out that there is a Palais style definition. At least we call it Palais style. So Richard Palais defined this Lie bracket version of exterior derivative definition, which was coordinate free. And in this field, that has become very popular, that all exterior derivatives can be written like this. So the Palais style definition says that if you have, let's say if you have an omega, which is living in, which is a K form, E-valued K form, then d nabla of omega, that's going to be a K+1 form. So, so since it's a K+1 form, it will take, I should tell you what it should do for K+1 vector field. And what it does is, it does this, so you delete one vector field at a time. And so if I take omega x1 and delete xi, and put a sign here, maybe I want to make it 0 through k. Let's do that. Then the sign looks nicer. So what do we do with this? Well, what is this? This is a section. So I can take a derivative. So I take the covariant derivative with respect to the missing vector field of this guy. So that's the first term. And so it's the covariant derivative along the missing vector field of this object, which is a section after I have fed it k vector fields, plus summation -1 to the I plus j, I less than j between 1 and between 0 and k. And this part has no derivatives other than the Lie bracket, which is a derivative, I guess. xi, xj, and x0, xi is missing, xj is missing. So we put in one extra guy and delete it to, so we are back to k. So this Lie bracket, this is called Lie bracket of vector fields, and it gives you a new vector field whose, when you act on a function to get the directional derivative, that's the directional derivative of this function minus that function. So this, if you wanted to do ordinary exterior derivative, all you do is write down exactly the same definition, erase the nabla from here, and instead of using the covariant derivative, just use the directional derivative, just use x on that. So x acting on this function, because then omega is a function, right? When you give enough vector fields to omega, it becomes a function, so you can just use x. So that was original Palais definition for exterior derivative. So we have that, and now let's talk about, because we want to do differential geometry and I want to get to the elasticity complex, hopefully. Let's, via double forms, let's understand curvature as an endomorphism value 2 form. So one vector bundle that we use often is the tangent bundle, and a connection on TM is sometimes called an affine connection. Let's call it nabla. Connection nabla on TM is an example of an affine connection. So for example, if you happen to have a metric and you take the Levi-Civita connection, it is a particularly nice affine connection. It's unique. It's compatible with the metric, and it's torsion-free. But let this be any connection on TM. There need not even be a metric. The TM is a bundle. It can be it can have a connection. So let it be that. So if you have that, then the curvature of the connection R of this nabla, you may or may not have realized is actually it's a endomorphism value 2 forms. So I will write those words and explain what this means. So there's a bundle called, so if you have a bundle E, there is also a bundle called end E over M. So this is called the endomorphism valued bundle, or endomorphism bundle, endomorphism vector bundle. And a section of this is actually a linear map at every point. A section of E is a vector at every point. A section of end E is a linear map at every point, which can act on sections then. So it's a field of linear maps. And if you write the usual definition of curvature for an affine connection, so notice that it's a 2 form, and it's endomorphism valued because you will feed it a third vector and get a new vector. So it is really the curvature we know as R is an endomorphism valued 2 form. It's an example of an endomorphism valued 2 form on the TM bundle. And the Riemann curvature tensor is just, if you have a metric, then it's R, X, Y, Z, comma W. But this to me is the more basic object, this endomorphism value 2 form. So that's what curvature is. It's an endomorphism value 2 form. So the curvature of a general connection on, so if we take a bundle and look at a curvature of a connection, so we're back to vector bundle E, and we're looking at we have a connection on E, and this curve, so some people write it with using F rather than R in physics. So F is a 2 form which takes values. It's an endomorphism value 2 form. And its definition is just d nabla square. So this separates all the stuff that one does with complexes from geometry, that you only get, you get sequences, not complexes. You don't get a de Rham complex, you get, if you want to call it, a de Rham sequence, because F of nabla is d nabla. So I'll just stop writing that. So F is d nabla 1 of d nabla of 0. So you might say, well, that looks like a second derivative. It's not, doesn't look like an algebraic operation. So let me convince you that this is actually an algebraic thing. It's not a derivative. So let's take d nabla E0 of a section. And so let's take, so I want to show that this thing is an endomorphism. It acts like a linear map. So I want to show you that if you take d nabla 1, d nabla 0 of F times a section, then there is no Leibniz rule. This turns out to be so this is what I'd like to show. So let's work with this. Start here on the left-hand side. So d nabla 0 of Fs by the definition is df tensor S plus F times nabla E of S, which by the way is just another name for d nabla 0, right? Right. So maybe I should first maybe write somewhere once we have a definition for d nabla, I should just say that what we can do is we can identify sections with 0 forms. And we get this sequence. And this isomorphism is that if I have a section, I can think of it as the constant tensor S, the constant function 1 tensor S. So it's a 0 form valued. It's a 0 form. It's a E valued 0 form. So this is the sequence we are looking at, and we are looking at the first 2 guys, but you can do any D square. So D square is going to turn out to be an algebraic operation. It's going to have this linearity property. So d nabla of Fs is that, and let's do one more d nabla of that. So that's d nabla of this plus d nabla of that. So just using the definition, the Leibniz property. So by the way, one can show that this Palais style definition satisfies the required properties. So by the way, there's a manuscript that Evan Golick and I are writing to explain various operations that are useful in this this construction that leads to things like elasticity complex, but in the presence of curvature. So so let's do the first one. So that's d square F, right? It's the ordinary D of the first guy tensor S minus df wedge nabla ES. The second guy is df tensor, wedge, df wedge nabla ES plus f d nabla 1 of nabla E of S. So this cancels with that. D square is 0. So we are left with f d nabla 1, and the nabla is, we can just view S as 1 tensor S and this as d nabla. So this is d nabla E. So I've been a little loose about one tensor S versus S, but you can make it formal. So you see, it's an endomorphism. It doesn't take derivatives when you do the second derivative because this cancels. So and there is the differential Bianchi identity in this world just says that one can define a d nabla for homomorphism valued things, and that's 0. So this is the structure we would like to reproduce in our structure preserving philosophy. So any questions about this so far? So let's now talk about a much simpler picture, which is discrete vector bundles with connection. Discrete connection. So for us, a discrete vector bundle with connection is a vector, a simplicial complex X. With a vector space of a fixed dimension EI at each vertex. And that by itself is a a very boring structure. What makes it interesting is what physicists have done in lattice gauge theory, which is that on each edge, you have one has a parallel transport matrix, or sorry, parallel transport map. Uij, so you read from right to left. This is an invertible map, and it maps the fiber. So these things we will call fibers, this vector spaces. It maps this fiber to that fiber. And there's a compatibility condition that if you go in the other direction, then it's the inverse of that. Now, if you associate every EI with a particular basis and Rn, so that's like picking a gauge. And then these Uijs just become matrices. So they are in GL D, where D might be the rank of this vector bundle. So imagine you have fibers, they are just, they are abstractly associated with each vertex. These fibers are vector spaces, and these maps tell you how to take this vector space to that vector space. A section is just, so we'll say, so we'll start using this terminology. So this will be sections, the space of sections. This is a choice of a vector at every point from this EI. So the covariant derivative information is captured in this parallel transport maps. And the covariant derivative, so before I say the covariant derivative, I should say, so we will also have with each, for each simplex, there is a special point let's call it something, origin or something. And in the first development of this theory, we will say that you have a total ordering on this. So assume for now, which we will drop later, assume that you have a total ordering on the vertices, like you have numbered your vertices from 0 to whatever. And this origin vertex is the smallest vertex, smallest numbered vertex on each simplex. So anyway, each simplex has some special point, and for now it will be, it seems to depend on the ordering and arbitrary choice of ordering, but so be it. We will remove that later. So the space of E-valued K cochains will be, if alpha belongs here, then this means that alpha takes a value, let's call it alpha evaluated on sigma. This is a K simplex, and let's say L is the origin. And so this is living this is in the vector space EL. So it takes a value at every simplex, and that value lives at the origin. So imagine every simplex has so you have a numbering, and every simplex clearly has, since you have total order on the vertices, every simplex has a unique lowest vertex number. And for bookkeeping or whatever, we have decided that that will be the place where the cochain's value will live. So it's an arbitrary choice for now. So so let's see what is the covariant derivative. So we would like this guy to map 0 cochains to 1 cochains. So since it's going to be 1 cochain, I should tell you what the values on the edge should be. And when you see it, you will see it's so silly looking. So this is your edge. And let's say I have transport map from 1 to 0. I do the arrow for the orientation just to remember which way I'm subtracting. And then you do a co-boundary with transports. So then the covariant derivative of this section evaluated on this edge is going to live at the lowest vertex of the edge. So we have to associate the value that the edge will take, the form will take on the edge. We have to associate it somewhere, and we've decided to pick the lowest. So we'll write that here. And that's simply almost S1 minus S0. The problem with doing S1 minus S0 is that this is your E0 and this is your E1, and it doesn't make sense to compare vectors living in different places. So you just bring it to 0. So that's your covariant derivative. And the extension to d nabla, let's say d nabla k, which maps ck xe to ck plus 1 xe, is the following. So d nabla k of some alpha, when I evaluate it on, that's a k plus 1, k plus 1 co-chain, so I need to give it a k plus 1 simplex.
Anil,
yes.
I think that half of the board might not be recorded.
Okay. I will continue on the other side then. Thanks. So we were doing d nabla of k co-chain, and we can do an example also. So the d nabla of a co-chain will be just, once again, the co-boundary operator with some parallel transports built in. And because of the choice we have made, only one simplex value will need to be transported, because everything else will be living in the right place. So let's say we want to define d nabla k mapping k co-chains to k plus 1. And d nabla of alpha evaluated on k plus 1 living at 0 is going to be alpha at 1 k plus 1. That lives at 1, so that needs to be transported. And after that, you have summation minus 1 to the I alpha 0, 1, I missing, I goes from 1 through k plus 1. But these ones already live at 0 because you're deleting vertices from 1 onwards. So this doesn't need to be transported. So it is just the co-boundary, except that one far simplex needs to be transported. So for example, let's say alpha was a 1 co-chain, and we want to do d nabla of that. So d nabla of alpha, we need to evaluate that on a triangle. It's going to live at 0. So let's do that and some orientation. So this will be alpha at 1, 2. So you delete one thing at a time. That lives at 1. So this needs to be brought to 0. So this was 0 deleted. Then this is minus alpha at 0, 2, which lives at 0, plus alpha at 0, 1. So these don't need to be transported because they're already living in the right place. So only the far simplex, opposite to the lowest vertex, that needs to be transported. So with just this simple structure, you can get a definition of curvature, discrete curvature. So we saw that d nabla square, so d nabla 1, d nabla 0 was the curvature endomorphism. Let's see what we get if we do this exercise for the discrete case. So we're going to do, so let's take a section. And do this D1, D0 of the section. So that's going to be something that lives on a triangle. So let's feed it a triangle. And it'll take a value at 0. So this is what we should compute. And out will pop a definition of curvature. So this is, let's peel off one thing at a time. So this is D nabla S at 1, 2 transported minus D nabla S at 0, 2 plus D nabla S at 0, 1. So let's work on the thing inside, and you get, this is S2 minus S1, but we have to transport everything to 1. So from 2 to 1. That's the first term. Minus, this is S2 minus S0, but we have to make everything live here, and you can't do it. You can't do this until you do the transport. And then plus, this is S1 minus S0 after transport. So this is U01, U12, S2 minus U01, S1 minus U02, S2 plus S0 plus U01, S0 minus S. So these cancel and these cancel. So what you're left with is U01, U12 minus U02. S2. So this intuitively makes sense to be a curvature, because what it's doing is not quite holonomy around a triangle, but let's take. So it's bringing the section, the vector living at 2 around the long way and comparing it to bringing it along the short. And this can be turned into a holonomy by multiplying by one more matrix, but this is what pops out. This is what we take to be curvature. So curvature in the smooth case was an endomorphism. It was a map from a place to itself. But in the discrete world, things spread out. Curvature is not an endomorphism. It's a map from one point to another. It's still a two-form, but it's a homomorphism. So we call it homomorphism valued forms. And now we are very close to getting Bianchi identity also. And then I will remove this restriction of having to have a total ordering on the vertices. So just like there were endomorphism valued forms on this bundle, we have homomorphism valued forms. And so that vector bundle comes with an induced D nabla. And so by the way, all this naturality stuff that we talked about with simplicial maps still holds here. You can define a pullback bundle, and you can show that the operators we are defining are natural with respect to pullback via simplicial maps. So the space C, K, X, E. So this is the space of homomorphism valued A forms. So these are maps from C something to C something plus K. And on a simplex, if you have, so let's take some B living here, or A. or B, let's say. So if you have something which is a K form, then if you give it a K simplex, then the value of B on a K simplex will be a map from, let's give it a particular K simplex. So will be a map from the highest vertex to the lowest, which we'll write as 0, K. And so homomorphism should act on fiber elements, on vectors. And that action is, let's say you have alpha belonging to CL, XE, and B lives here, then B times alpha or B cup alpha. So this takes a value on a K plus L simplex. And you take B and you give it the first K guys, and this is a map from K to 0. And you take alpha and you give it K to K plus L. And that lives at K. So you have this vector at K which gets transported back to 0. So there is in the smooth theory, there is a D nabla defined so that you can talk about Bianchi. So let's define D nabla for so what this does is, so let's say you have A is a homomorphism valued K form. Then what is its D nabla? Its D nabla will be a K plus 1 homomorphism valued guy. So by the way, the theory that I'm building, it's very simple, but finding the right definitions was the key. And then everything fits together and all the operators have the structural properties. There are some things you don't get, like you cannot antisymmetrize because you get a curvature obstruction to doing that. And so it's a matter of being structure aware. So what does this do? So this, if I give it a K plus 1 simplex, this will be a map from K plus 1 to 0. And this will be equal to, take A, again, just almost like the co-boundary. So that's a map from K plus 1 to 1. But we want a map to 0, so you map to 0. And then you have A on 0, 1, I missing K plus 1. That's a map from K plus 1 to 0 already, because we are only going from 1 onwards. But we don't go all the way to the end. Because if you remove the end, you have to treat that specially. And then finally, we have the last term where you evaluate A on that part. And now you have to transport from K plus 1 to K, because this is a map from K to 0. So that's the definition of the exterior derivative, the covariant exterior derivative of homomorphism valued cochains. And with this, let's do discrete Bianchi identity and then move on to double forms, end with elasticity. So we have our curvature homomorphism, which is a two form and homomorphism valued. And we want to do the D nabla of that. So it will be a 3 form. So we should evaluate this on a tetrahedron. So this will be a map from 3 to 0. And just using the definition, we have F at 1 to 3, which is a map from 3 to 1, which needs to be brought to 1, minus F at 0 to 3, which is a map from 3 to 0, plus F at 0, 1, 2, 0, 1, 3, sorry, 0, 1, 3, which is a map from 0 to 3, minus F at 0, 1, 2, which is a map from 2 to 0, so we need to add a map from 3 to 2. So that's, but we already know what the curvature definition was. The curvature evaluated on a triangle was going the long way minus going the short way. So let's substitute those. So this is U01. So this will be U from going the long way minus the short way, minus that, plus minus so now let's stare at that. So here's a 0, 1, 1, 2, 2, 3. 0, 1, 1, 2, 2, 3, plus minus. So that goes away. 0, 1, 1, 3. 0, 1, 1, 3. This one is a minus, that's a plus. So that goes away. Plus 0, 3 minus 0, 3 goes away. Minus 0, 2, 2, 3. Plus 0, 2, 2, 3 and a minus. So indeed, one has the discrete Bianchi. So that's probably all I want to say. There's a lot more, which is on an older archive paper, which we are revising. So this one was posted in 2021 already, or 2023, I think. And so how do you remove this ugly requirement of having a total ordering on the vertices? So that, once again, subdivision comes to the rescue. So let's take a triangle and subdivide it. So take this triangle and do a subdivision. Take any point, doesn't have to be the circumcenter. But the fact that you could use a circumcenter means that later as we develop the theory, we might be able to bring in the metric of the manifold also, just like we did for the ordinary exterior calculus. So now notice that if you look at any triangle in the subdivision, or any simplex, every vertex is at a different dimension in the subdivision. So this is the center of a vertex, center of an edge, center of a triangle. Look at this edge, center of edge, center of triangle. Look at anything like maybe this one, center of vertex, center of triangle. So they are all, the vertices are all at different dimension. So there's a canonical local ordering without imposing a global ordering. Every simplex can be totally ordered in a canonical way. So what we do is we choose highest dimension to lowest ordering. And if someone gives you a simplicial complex, you do one subdivision and now you have a canonical ordering. And you can then do your theory, do your transport maps on that subdivision and then accumulate in the original one. And the beauty of this is that, let's say, so let's call this 0, 1, 2. This is center of 0, 1. And this is center of 0, 1, 2. So notice that for all of these triangles, the lowest vertex is this, because we have ordered from highest dimension to lowest. So C012 is ordered less than C01, ordered less than 0. This is a partial ordering because you can't compare this and this, but in any simplex, it's a total order. And since all of them, so that means if you have a 2 cochain for these small triangles, they will all live here. So you can add them and reconstruct a cochain for the bigger triangle. And this also allows you to do a curvature on any codimension 2 thing. So if you have a tetrahedron, then there'll be an edge. The edge will have a dual. The dual will be 2-dimensional. It will be made of 2 triangles. One that goes from the middle of the edge to the triangle to the tetrahedra, and then the other way. So you can define the curvature on these small triangles. So that matches more nicely with what one would like to do, for example, in higher dimensions. And so, for example, if people associate curvature on triangle meshes at the vertex, at least Gaussian curvature, so the intrinsic curvature. So you could do a subdivision. When you do the subdivision, you would have small triangles around the vertex. So you could make, it was very unnatural to have the curvature only available on triangles, but now you can do it on any codimension 2 simplex, because its dual will be dimension 2, which will have triangles. Anyway, so I'll stop there for the discrete stuff, and now switch to double forms and hopefully elasticity. So double forms were introduced by D'Arcy in the 50s, and they have been used in geometry analysis in many places. And an Indian mathematician, Shripad Kulkarni, he wrote very beautiful papers. There's one called On the Bianchi Identities, where I learned about this name, double forms. We were calling it something else. So double forms, the space of double forms is written like this. And elements of this are combinations of terms like this, where alpha is a K form and beta is an L form. And if I give you K vector fields, then this alpha will consume them and you'll get an ordinary L form. So this is the sense in which, so we also call it L form valued K form. If I give you K vector fields, they will be consumed by the first part and the result will be an L form. So this is actually, it's a short way of writing sections of this bundle. And what we had earlier was E form valued guys, and I didn't write it, but those were. So this is a special case of that, where E is this bundle of L forms. So here is where you use, so in the general theory of vector bundle E, you were given a connection. Here you are forced to use affine connection on the tangent bundle. So it doesn't, you can slowly add restrictions. So for example, for some of the things that you want to do in constructing elasticity complex, you do require torsion freeness and things like that. So slowly you can figure out what are the minimal requirements for doing various things that one wants to do. But so remember that the covariant derivative was defined by using a covariant derivative on E. So now we will need a covariant derivative on L forms, on ordinary L forms. And once again, Leibniz rule comes to the rescue. So how do you, given an affine connection, on Tm, on the tangent bundle, how do I define a covariant derivative for K forms? You do that by requiring Leibniz rule in the following way. So you have a K form, ordinary L form, let's say. Yeah, let's call it L form. So you have a ordinary L form, and you want to define a covariant derivative for this bundle. We were writing E, so technically I should write lambda L T star M, but that will be a lot of writing. So I will just write. So we'd like to define a connection and a covariant derivative on L forms. So let's say you have a vector field Z and you have L vector fields. So if I take the directional derivative of this function along Z, so the directional derivative will be the covariant derivative on L forms along Z of beta. This is what will define it, x1 through xl, plus summation beta x1, the ordinary, the affine, the covariant derivative coming from the affine connection of xi. So this is the object we were trying to define. So the definition is this minus that. So by requiring Leibniz rule, you can define covariant derivatives for ordinary L forms. So once you have the ordinary L form, then I erased that definition, but you do a Palais style definition again, and just replace in that definition where you saw the covariant derivative which is of the vector bundle E, you replace it by covariant derivative of this vector bundle. So this particular code. So it's exactly the same definition with the Lie brackets and whatnot, and you can do that. So you can now do D square, and you will find something like this. I don't know if I can get the formula right, but if you do D nabla, so with that, once this is defined, you can define D nabla KL. So this will be, like I said, exactly the same or maybe I should just write it out. So D nabla KL of, let's say, some omega. So if you have a double form, if you have a double form omega, a KL form, so it's L form valued K form, then its D nabla will live on will live in K plus 1 L. And so its value on K plus L, let's maybe take 0. So its value on K plus L vector fields will be equal to summation minus 1 to the I going from 0 to K. So now we can use the covariant derivative with respect. So, okay, so this also needs L vector fields because that's a K plus 1 L form. So I have to give it K plus 1 and L things. So for forms, we always write arguments. For these double forms, we write the set of arguments separately. So the K part gets K things and the L part gets L things. So this will be the covariant derivative that I just defined along xi, where xi is missing from this. By the way, I wish I had the videos like the previous speaker had, and he was clearly very engaging. And I'm sorry I'm not like that, but this is what we have. So this is that, then plus summation minus 1 I plus j. So I plus j, I think, and I and j, I less than j, 1 to 0 to k. So it's exactly the same definition that we saw, Palais style definition with xi, xj, x0, xi missing, xj missing. The only thing we have changed is this covariant derivative. In the ordinary exterior derivative, this would be xi. In E-valued bundle case, this was nabla E xi. In double forms, it's nabla L xi, but otherwise the definitions are the same. So what happens if you do d nabla square? So if you do d nabla of some k and k plus 1, let's say, then what you end up getting is something like, so you have, so then let's give it x1 to k plus 2, right? K form becomes k plus 1 becomes k plus 2. Yeah. So let's give it k plus 2 arguments and then L arguments. And how does the curvature show up in this? We said d square is curvature. So where is the curvature going to come? So the curvature will come up in, there will be minus summation minus 1 I plus j minus 1, I think, I less than j less than equal to k plus 2 less than or equal to 1, omega, these two will be missing. And there will be another summation over m going from 1 to L. And that summation will have y1, then the curvature tensor of xi, xj applied to ym. So this is the precise way in which d square is curvature in the case of double form. So, okay, why are people so excited about double forms? Everybody is writing, well, everybody that I know is writing papers on double forms. Because so apparently stable mixed elements for linearized elasticity were not known for decades. And Doug and Ragnavinther solved that problem in 2002. And they did it by using something called an elasticity complex. And then slowly it became clear over the years that this was part of a construction, or it's inspired by a construction that's known in geometry. And it's, I guess now people call it inspired by that, not exactly that. So what is this name, the name of this guy, and why is it relevant to elasticity? Let me try to sketch quickly. Yes. Yeah. On the covariant derivative, on this one, yeah, there is no sign on that. Yeah, it's just doing, it's like doing a product rule. So derivative of this, just think of it as derivative of this plus derivative of this with these plus this times derivative of this plus this times derivative of second. So just that, yeah, satisfying the line.
And in the middle portion,
yeah,
which is the covariant derivative on k plus L or KL double form.
Yeah.
The last sum in the last term.
Yeah.
Omega should be eating K plus L vectors, right?
Uh,
In that term.
so omega is a KL form.
So I think there should be more Y1 through YL as well.
Oh yeah, that's right. There should be these. Thanks. Yeah. So then a paper was published a few years ago by Kaibo and Doug Arnold, I guess in that order, called Complexes from Complexes. The paper Evan and I are writing is called Sequences from Sequences. But theirs was using coordinates. So we said without coordinates. Sequences from sequences without coordinates.
And Anil, maybe can you say a bit more about what you mean by, you said that the finite element formulation for linearized elasticity didn't have a stable.
Yeah. So I'm not an expert. I'm just learning. So I don't know the finite element literature in linearized elasticity. But apparently for mixed formulation, I don't know whether it was displacement and stress or which formulation it was, but it was in 2D. It was, it had too many degrees of freedom. It's not used, but it was the first theoretical solution.
Compressible as well, not with constraints of compressibility.
Sorry?
This was in the context of a compressible solid or compressible linearized elasticity. Because if you have constraints like divergence, like
I don't know if it was, I think it must be compressible. Okay. Otherwise you would have incompressible constraints on it. Yeah. So this paper introduced how to do this in Rn. And I'm going to sketch this idea in, we are trying to do this in a general manifold with non-zero curvature, but I think maybe it's best to just do it using their setup, but in a slightly more different way, right? So they are, for them, M is R3 or Rn, sorry. So M is a, let's say, open subset of Rn. The manifold is open subset of Rn, and the connection is the one coming from the Levi-Civita connection of the standard Euclidean metric. So in their case, when they do a denabla of something which looks like F dxi1 wedge dxik tensor dxj1 dxjl. So when you do that product rule where you do d of this tensor that plus this wedge covariant derivative of that part turns out to be 0. So this is simply df wedge dxi1 wedge tensor. The second term is not there. So this is the special denabla for which this construction has been completed, and there is lots of wonderful results. Finite elements have been found for it. There are 2 very good papers on finite elements for double forms. So one is by Yasha Barchenko, Kogan, and Evan Golik, and the other one is by Kaibo Hu and Tinglin. So both these papers are very long but fantastic papers if you want to learn more. So I'll write it as lambda rather than omega because we are working in Rn, and let's just do it for R3. So this construction is called the Bernstein, maybe I should write it here. So it's called BGG inspired. And this name comes from Bernstein, Gelfand. And this is an Anil's paper in 2001 by Andreas Chapp and Slovak and Souček or Suček. I don't know how to pronounce the names, but Chapp I know because he was one of the speakers in the workshop we had in Chicago recently. So there's a paper by this name, and this is the construction inspired by that. And so what you do is you write down, so the idea is that we know how to do DRAM. What about other stuff like elasticity, biharmonic equation, so on and so forth? So that's what, this is the answer to that. This is the answer to that in Rn, and we are trying to answer that, and others are in general, in the general case. So you write down 0 form valued 0 forms, 1 forms, 2 forms, and 3 forms. And you have these D-nablas. And let's say you have zeros here, the 0 maps. Then you write down a square grid like this. So now we'll have 1 form valued guys. We'll have 2 form valued. And we have 3 form valued. So these are the standard D-nablas. So you have 4 copies of DRAM complex. And if you had n-dimensional space, you'd have n copies. So it will be an n by n grid with zeros at the end. But the beauty comes from these operators that were that have been known since Calabi wrote a paper in 1950s or 60s. But I learned about it through these papers and then found it in Kulkarni's papers. So these are called these are called Bianchi sums. I'll still use S for that. So like this is S01, this is S11, this is S21, and so on. So there's an S operator everywhere. And it's a purely algebraic operator. And the definition is as follows. SKL of some omega gives you a K plus 1 L minus 1 form. So, so here's the definition. So since it's a K plus 1 L minus 1 form, we should give it K plus 1 L minus 1. So let me, if that's okay, can I just finish the story with this? Okay. So this is, what you do is you just take, it's a very algebraic construction and amazing that it works. Omega only needs K and L, and what you do is you move 1 over here and sum over all. So you have omega, subtract the ith guy, and move it. And this I is between 1 and K plus. So if you have a torsion-free connection, which if you had Levi-Civita, of course you will do, then the following will be true. There is a commuting diagram in the parallelograms. ES plus SD is equal to 0. And there are adjoint operators, and those are also defined completely algebraically, but they turn out to be adjoints of the S operators in the L2 sense. And the way you prove it is using that contraction formula that I showed you. I mean, that's one way to prove it. The wedge contraction duality is used, can be used to prove that. So this is very important. And the other important thing is that in this diagram, this is an isomorphism. This is an isomorphism, and that's an isomorphism. And everything to the left of the red arrow is injective, everything to the right is surject. So these are the properties, and you can show that these maps have this property. So what you do is, let's say if you wanted to do elasticity, you would focus on these two. If you wanted to do biharmonic equation, you would do, what you would do a zigzag. So I should get a good 2 colors and quickly do that. So for biharmonic, you would do a zigzag here and cross out certain things. So I'll just do it for elasticity here. So what you will do is you will start here, and we are going to do a zigzag at the isomorphism. You project to the kernel of S star. And since I'm out of time, I can't show you, but the kernel of S11 is symmetric 1-1s. And then the next one is this, and this also you do projection D nabla. Then actually no, this you don't need to do anything. So this is D. You cross out this space where the zigzag is happening, and then you continue along here. So you get this diagram that I will draw here and end, and I'll just write down the elasticity things that lie there, and those are as follows. So you have 0, 1, 1, 1. This becomes the symmetric gradient. And then this is D, S inverse D. This is the ink operator. And this is 2, 2. And this is the divergence. And so this is, I guess, some people call internal strain and internal stress, load, and displacement. But so I don't know about all that stuff, but if you work this out, this will be the ink operator, this will be divergence, and this is symmetric gradient. And it's a complex in the sense that ink of this is 0 and D of this is 0. But what happens when the complex property is not true is something that we are trying to work out. And finally, I wonder if this is a good picture for elasticity, for linearized elasticity, that you have, this is D nabla sim. This is where displacements live. This is linearized strain. This is hot star with C, which has the mu and lambda somehow. This is only, it's a hot star on the first leg. That's what you do in double forms. So that's a 1 form value 2 form. And stress should be n-1 value, n-1 form valued 1 form, because it will tell you the force acting across something. And then you have a D nabla here, and you get a density, a 1 form valued. So this could be the body force. So anyway, I'm sorry for going over, but I'll stop here.